In each of the first 3 tutorials, we analysed the triangular geometry of rotating a point around a single axis. This tutorial looks at how that geometry becomes combined as a result of rotating around the X, Y and Z axis in that order, one after the other. If you watch this animation, you can see that the local x-axis rotates around the global x-axis, which is because it rotates first, but because all 3 axes become rotated by that same angle, the y-axis rotation is therefore tilted by the x-axis rotation angle, and the z-axis rotation is tilted by the combined x and y rotated axes. We'll start by examining 2-axis rotation, by first rotating around the x-axis, followed by rotating around the z-axis, and then in the same manner we'll examine XYZ 3-axis rotation. The 2 animations show how the basis vectors become tilted. This vector illustration reveals how each of the individual vector components are added together to also produce the resulting vector. This vector illustration reveals the 5 triangles which together form the geometric relationships of the combined rotation. The x value of the x-axis is the adjacent side of this triangle, which was produced by rotating 25 degrees around the z-axis. Notice how the x-axis rotation makes no difference to the x value. The y value of the x-axis is where it starts to get interesting, because we have cosine and sine being multiplied together. If there was no rotation around the x-axis, then this vertical component would be at its maximum value, because sine 25 degrees would produce a vertical opposite side for the larger triangle. However, the x-axis has been rotated by 35 degrees, and therefore the vertical component is the adjacent side of this smaller triangle. The key thing to notice here is that this white vector exists as the opposite side for this triangle, but as the hypotenuse for this triangle, which is the reason the triangles are related by multiplication of the sine and cosine terms. The z value of the x-axis is calculated in the same way, but is the opposite side of the small triangle. Essentially, the y-axis rotation consists of exactly the same logic as for the x-axis. It's just that different combinations of sine and cosine apply to each triangle of vector components. Let's finish analysing this xz combined rotation by noticing that the x value for the z-axis is 0, and that for the z-axis to produce a non-zero x value, either y-axis rotation is required or the z-axis rotation needs to happen before the x-axis rotation. We can easily check the results of the calculations against the orange vertex location values in Blender. Next we'll look at 3-axis rotation by rotating around the x-axis, then the y-axis and then the z-axis. Just like for the XZ rotation, the animations show how the basis vectors become tilted, and the vector illustration reveals how each of the individual vector components are added together to also produce the resulting vector. I'll explain the y-axis first and then the x-axis because it's a little trickier to see. And then we'll finish off by taking a very quick look at the z-axis, but let's just have a quick look around the whole structure first. So for the y-axis x value, we have the opposite side from the sine of this triangle, which becomes reduced in length because of rotating around the y-axis. And also notice how the x-axis rotation makes no difference. The geometry for the y-axis y value splits into 2 separate vector components, because the larger component isn't affected by the y-axis rotation, unlike the smaller component. The larger component is the cosine for this 20 degrees triangle multiplied by the cosine for this triangle. The smaller component is the sine for this triangle multiplied by the sine for this triangle multiplied by the sine for this triangle. For the y-axis z value, it's only the leftmost terms that are different in contrast to the y-axis y value, this one being cosine instead of sine, and this one being sine instead of cosine. Cosine gets us the larger distance and sine gets us the smaller distance. For the x-axis x value, it's the cosine of this triangle multiplied by the cosine of this triangle. There's no x-axis rotation involved, so the red basis vector first rotates around the y-axis and then around the z-axis. The cosine of the vertical triangle exists as the hypotenuse for the horizontal triangle, which is where the multiplication is represented geometrically. For the first component of the x-axis y value, the cosine of this 20 degrees triangle exists as the hypotenuse of this triangle, and the sine of this triangle exists as the hypotenuse of this triangle, of which we use sine to get the opposite side. Then, similar to the y-axis analysis, this second vertical component splits away because it also isn't affected by the y-axis rotation. Out of these two identical striped vector representations, this one is just a copy, which I created when I was working out all the geometry, and so I've decided to leave it in place for illustration purposes. For the x-axis z value, it's only the leftmost terms that are different in contrast to the x-axis y value, this one being cosine instead of sine, and this one being sine instead of cosine, exactly like was shown earlier for the y-axis. The z-axis x value is determined by only the y-axis rotation, and the z-axis y value and z value are both determined by the x-axis rotation multiplied by the y-axis rotation. Finally, we can once again check the results of the calculations against the orange vertex location values in Blender. In the next tutorial, we'll be looking at how to represent rotation transformations with matrices, and how to construct scaling and translation matrices. If you found this tutorial interesting, then please click on the like button, and please don't forget to subscribe if you'd like to see more. Cheerio for now.